Now we're going to calculate an iterated integral, and what we've got is the integral from 1 to 3 of the integral from 1 to 5 of the natural log of y divided by x times y dy dx. This means, of course, that y goes from 1 to 5 and x goes from 1 to 3. We aren't going to do any drawings. What we are going to do is split this up. The integrand can be expressed as a function of y times a function of x. So I'm going to write this as the integral from 1 to 3 of 1 over x dx times the integral from 1 to 5 of the natural log of y over y dy. And we'll integrate these separately. The integral of 1 over x dx is the natural log of x. That's going to be evaluated from 1 to 3. And then for the second integral, letting u equal the natural log of y, we get that du is equal to 1 over y dy. And so we essentially have a u du situation. And the integral of u is 1/2 u squared. So we're looking at 1/2 times the natural log of y, that quantity squared, evaluated from 1 to 5. Since for both terms we have to consider that the natural log of 1 is 0, we end up here with a final result of 1/2 times the natural log of 3 times the natural log of 5 quantity squared. I would like to point out here a note that the natural log of 5 quantity squared is not the same thing as the natural log of the base 5 squared. In the second case, it would be the natural log of 25, or we could pull the 2 in front as an exponent. But in what we have, the quantity of natural log of 5 squared, that means whatever you get out of the, say, calculator for natural log of 5, you would square that result. Finally, we're going to look at calculating a double integral over the region R of y plus xy to the negative 2 dA, where R is equal to the set of ordered pairs xy such that x is between 0 and 2, and y is between 1 and 2. I would like for you to pause the video, come up with the answer, and come back when you're done. I went ahead and set this up using the order dx dy. So I have the integral from 1 to 2 of the integral from 0 to 2 of y plus xy to the negative 2 dx dy. Integrating the inner integral with respect to x and holding y constant, so basically doing a partial integration, results in the integral from 1 to 2 of x, the quantity of xy plus 1/2 x squared, y to the negative 2, and x is going to go from 0 to 2, and then we'll still integrate with respect to y when we're done simplifying. Plugging in 2 in place of x will give us 2y plus 2y to the negative 2. Plugging in 0 in place of x zeroes out everything. So we now have the integral from 1 to 2 of that 2y plus 2y to the negative 2 dy. Integrating with respect to y gives us y squared minus 2 over y. And we're going to evaluate that from 1 to 2. Putting 2 in place of y gives us 4 minus 1. Putting 1 in place of y gives us 1 minus 2. And subtracting 4 minus 1 minus the quantity of 1 minus 2 gives us a result of 4. I chose to do this using the order of integration dx dy. We could have just as easily set this up, and maybe you did, as the integral from 0 to 2 of the integral from 1 to 2 of y plus xy to the negative 2 dy dx. The order of dy dx and dx dy only matters up to the limits of integration, and Fubini's theorem tells us that setting it up that way would yield the same result of 4.